One of them, a very recent one today, and it's going to show that even very old problems sometimes allow for very good insights. So
thank you, Ingo, for the presentation, for the introduction. And well, before I start, I want to say that yes, well, I'm there, but because I present this work, but this work has been doing together with Miguel, and you know, and also with Ingo, and that this work has been not possible without also lots of discussions and experimental advice from Daniel, so here, and with Thomas on the scaling and on lots of discussions about chaos. Okay, so yeah, the title of my seminar is Scaling Optical Chaos in Delayed Feedback Semiconductor Lasers, and actually, why semiconductor lasers? Because these guys have been with us for more than 50 years already, and they have evolved from this kind of weird experimental lab only device to this nice, cheap, efficient, fast and powerful encapsulated devices that are now ubiquitous in many applications in industry. Okay, of course, they don't need to be always so nice. Already in the 70s, very early, it was discovered that they showed instabilities due to delay of some kind of feedback. And I add here this figure because, I mean, feedback you can have everywhere from lots of sources. So even you want to couple the light of the laser to fiber, or you want to detect it, you can have any reflection. And that's like the source of instabilities, or the possible source of the instabilities. No? So this had been a problem. You know? That's a problem to solve, let's say. Many solutions, many studies. The thing is that when a problem goes for so long time, I mean, already since the 70s, it turns, usually turns into not only a problem, but into a field, no? Let's say field itself, so something useful you can use. So delay-induced instability basically has become a field in itself of study. Okay, and I've included here some applications related with our laboratory. Let's say with the work we have been doing in our labs of encrypted communications. Also, delay coupled lasers have been used for tuning the coherence length of light. Its inherent randomness, the chaotic dynamics randomness, has been used also for random bit generation, and also recently, let's say, cluster of applications is using them for neuroinspired information processing. Okay, if you like to see a compendium of all these applications and dynamics and all these things about this system, I mean, I refer you to this recently published review of model physics. And the idea I want to transmit is basically that understand and control the dynamics is important. So understand which dynamics we have and control them. So go to one, so classify classify dynamics in regimes, go to one regime, the other. So to use them for applications is important. Okay. So now I outline a bit the contents. No. So first I will review some classifications of the feedback regimes. Then I will relate the parameters used in these classifications with characteristic timescales, okay, of this system, okay, and use these timescales to define the feedback regimes, okay, to showing that there are some similarity properties, okay. Then from this we will show the relation they have with the transition in strong weak chaos regimes in real semiconductor lasers. Then I will, including all the timescales we have talked about, show how the full dynamics can be scaled. Okay. Just to complement, and I don't think that this is a kind of only bizarre experimental results. These are supported by numerical simulation. And finally, we will extrapolate partially these results to quantum dot lasers. Okay, different kind of lasers than the ones we will talk most of the seminar. So, what's the experimental setup if you want laser? You want feedback, controlled feedback. Okay, I've just shown here the schematic, but I've also wrote it because I could. No? So, because this kind of setup is exactly the setup we use. Okay, for adding feedback to a laser. So, if you want later, after the seminar, I can explain you in more detail on board the elements. Let me now refer to them here only. Okay. So we have the laser diode. Okay, here in the mount. So you can address the current, you can address the temperature, so you can control it. Okay. And then the idea of having feedback is having a mirror. No? But we use standard telecom components here, and they are fiber components. Okay, which is very useful for applications of this world. And what we do is not to put a simple mirror, but for full control, what we use is a loop. Okay, and that's why we use this element. So a circulator allows us only one direction, and this one direction that defines the delay time. We control the amount of light, so what we will call feedback strength, the polarization of light, which is important because in fiber speeds to be controlled, and also with one element that we split part of the light for detection. Okay, that's basically the introduction of to what experimental setup. So feedback looks like. No? So which are the main effects of feedback on lasers? And this is experimental data. So first effect that we see is, well, here from red to black. So red is minimum feedback and black is maximum feedback. Let's say minimum feedback is solitary most. Okay. So what we have is first the reduction of the lasing threshold. Okay, so feedback reduces losses and threshold decreases. Second effect, and that was already early classified in the seminar paper as coherence collapse. So your narrow line width source broadens, so the coherence of it collapses. No? That's why the name, and it goes from some hundreds kilohertz or megahertz, few megahertz to tens of gigahertz. No? So more than 3 orders of magnitude broadening, and that of course was the main warning, no, for first applications of lasers. No? So low coherence, and also the instabilities generated by feedback are reflected in the RF spectrum. No? So in intensity fluctuations we see. So more feedback increase the spectrum, the intensity spectrum of the laser to tens of gigahertz. Okay. So
sorry.
Yeah.
Yeah. So that the radio frequency that's simply the optical spectrum is that the case. So the scales are.
See, so this is the optical spectrum. Basically, broadens. Maybe more. Okay.
So what that means? I'm sorry.
More than 10.
I'm not familiar with the frequencies. But I mean, that's only the tails of that, or what is that? Is that there is another emission down the.
No.
You put both in the same scale, so you have another emission very down at radio frequency. Is that what you meant?
No. This is the radio frequency signature of this spectrum detected with a photodetector. I mean,
Spectrum of the intensity fluctuations.
yeah. So and also limited in bandwidth. So I mean, we have here. I mean, that's not limited. I mean, that's actually limits the resolution. But here is 13 gigahertz. So.
Probably the main difference that this is the optical one is centered at a very high frequency, and the other one is centered at zero.
Yeah, sure.
Is this the main difference?
Yeah. Actually, this is. Yeah. So this you could put in nanometers, for example, no? So we put easy gigahertz.
The optical spectrum is the spectrum of the electrical field. The other one is the spectrum of the intensity of the field. So one is the spectrum of a converse value, the other one is the spectrum of the real intensity. The intensity of the field. Okay? That does not contain the information on the field.
Okay, that's not what they information on the field.
On the frequency.
Okay. So, yeah. Even very early classifications of the dynamics, of the instabilities in the dynamics, so was with the state-of-the-art technology, no, by the moment. So in this one, they characterize the first one we have reference is they characterize the spectral features of the feedback, no, on the lasers. And basically, in this region I shaded here, the region 4 is the one that shows the instability. Okay, so you see more than 3 decades of feedback ratios or feedback strength, and during these 3 decades they saw this evolution, and then collapsing again into instabilities, into solitary emission. So the thing is that basically they characterize this with the external cavity length and the strength of the feedback. Okay, so they use these two parameters to characterize this. Later, when more than 10 years later, when faster scopes became accessible and higher bandwidth detection also, so people tried to characterize not only the spectral features, this coherence collapse, but also the intensity fluctuations. So the dynamics in the intensity domain for lasers with feedback. No? So basically, here we see another characterization. So it's injection current versus optical feedback strength. Like before was the feedback strength, no, in the vertical axis. It misses the external cavity length, okay, but is already a very signature of the different dynamics identifiable in this setup. Keep in mind that most of the dynamic regimes, of the dynamic range were occupied by dynamics faster than what was able to resolve. But what have in common these two characterizations is that they use the state-of-the-art technology, okay, at the moment of classification. They were based on the observed dynamics, and also they needed, they used different parameters, okay? One used injection current versus feedback strength, the other used external cavity length versus injection current, but missed the other one, no? And there were discussions about this, but basically we want to use these 3 ones because, I mean, the question is that if we can go further, no, than these kind of classifications in bidimensional bounds. So what we will do is precisely to actually look into the different time scales related with these parameters and try to characterize the feedback regimes with these time scales. Okay. So for this, I want to introduce you a bit the different time scales present in a system's laser feedback. So first, without any kind of feedback, you already have the dynamic time scale. No? So the characteristic frequency response of the laser to small perturbation, which is the relaxation oscillation frequency. This is experimental figure, again, this optical frequency axis. And you see at some gigahertz, 2, 3, 4, I mean, depends on the current, the value of the relaxation oscillation frequency. That we relate with the first, let's say, time scale. No? Second one is when you add feedback, you have a certain delay time, as pointed before. So it's this other time scale. Here I reflect this in the intensity spectrum. And these are the signature, so the resonances of the characteristic when you have this time scale. No? So between the different modes, no? Different solutions. So what is interesting, or the key idea here, is that these time scales are characteristic, no? Are common in lasers with feedback, so in semiconductor laser with feedback. So we will try to use them, no? For our characterization. And this is this slide with equations, with model, no, present. I have, that's why I put big font size. So the thing is that to characterize its evolution, I think is easier with rate equation model, with a model present. So this is ubiquitous again, Lang-Kobayashi model, so rate equation model for a laser with feedback. I shaded the feedback term just because only with the rate equation for the semiconductor laser we can obtain the expression for the evolution of the relaxation oscillation frequency. Okay, so this is the only parameter that varies. The other ones we can consider constant, and is the excess pan current, so the pan current above threshold. Okay, and already gives us a dependency. So what we were looking for. So characteristic time scale depending on a parameter that we can control. Right? That's one. The other one related with the delay coupling term, which is the external cavity time, so the delay time is already present here explicitly, so this tau. And also I want to mention that this is the feedback strength. Okay, so I don't explain fully the equations, but at least the important terms we will use are explained. Okay, so now we have introduced two time scales. Oh, three, because I promised three. But the third one, which was not considered in many studies, I mean, we will show that it's becoming, or is actually a key time scale, okay? So the thing is that you have, one is the external cavity delay time, another is the relaxation oscillation frequency, so a kind of time scale also. Third one is the one that you only can resolve if you resolve enough well, or with enough precision, the shifting of the maximum of the extension of the optical spectrum with feedback strength. Okay, so this is experimental data. Basically, here we see that from low, almost no feedback, to maximum value of feedback in this figure, the spectrum drifts here, and the maximum drifts also with the feedback strength. Actually, there is an analytic expression also derived from the previous equations that already guides us how this changes, okay? But we'll also characterize this experimentally. So, and reconcile it. So it's not. But it's nice to have also the expression to confirm its validity. So this frequency here, which I claim to be the third time scale, is basically dependent, so it's proportional to the feedback strength. Okay. This parameter here, which I've not introduced before, is actually the alpha factor, the length enhancement factor, which is the coupling between the carriers and the field. No? So represents the coupling of frequency in a semiconductor laser. Is related usually with the susceptibility of the laser also to feedback. Okay, and we will see its role later also. So just as one inset here, okay, because we have this expression. So I say, yeah, this frequency, this time scale changes with the feedback rate, but that's not how I will present in our experimental data. So that's why I want to make just this brief inset here. In our experimental data, we control the feedback strength with an attenuator, which is this guy here, okay? And actually, what we read out from this attenuator is the attenuation in degrees. So it's only to mention this because it will not change linearly; it will change with a logarithm relation, okay? And just as an indication, calculating the maximum feedback rate in our setup is this value, which is more important for people from simulation. I mean, but is something we know as a reference, no? And then we always have this maximum, and then we decrease with attenuator, okay? Well, so now it comes the key question. So once we have identified the time scales, what will be the relation between them, no? So, and how this affects the dynamics. So the thing is that if you remember the spectra I showed before, now these spectra just shifted and put in a color scale, and with much more of this spectra. So actually this is stacked lots of optical spectra, and the only parameter change here is attenuation, so the feedback strength, okay? And what we see here is, so now we really see the transition between feedback regimes, or between different feedback conditions, from weak, very weak feedback, to intermediate feedback, to strong feedback. And we can also identify the different frequencies here. This one, simply the optical frequency of the laser, okay? So if you have no feedback, you have solitary laser here. Once you start adding feedback, you have an amping of the relaxation oscillations. Okay, so these two lobes you saw before in the figure for the solitary laser, now they are undamped, and they have harmonics here. And as long as the feedback, so the attenuation, the feedback is increased, the attenuation goes to 0. Basically, we see that in the region of crossing of these two frequencies, the signature of the damping of the relaxation oscillations drops. The two frequencies merge, and you cannot identify any longer a leading frequency, let's say, in this part of the spectrum. 4, then we increasing even more the feedback strength, we again see the signature of different frequencies appearing. Okay. Finally, in this region here, simply the laser is not stable any longer, so it gets stuck into this high gain, into these modes in the high gain region. Okay.
Where in this diagram is the feedback time? There is inverse of the feedback time, the frequency of the feedback.
Well, yeah, it's not evident here, but I mean, we are changing the parameter that will be related. So later I will come to this point, but I mean, that will be, I mean, right now I'm only showing how the transition is. Then we will play with the time scale. Okay. So this figure is, I mean, again, it's only possible with actual state-of-the-art technology because this requires high resolution. So in this case, 10 megahertz resolution for the optical frequency with large bandwidth detection. So you can detect more than 3 orders, well, 3 orders of magnitude difference, no, between the high resolution and the whole bandwidth. And even we can resolve.
The horizontal line that you go there.
Oh, no, forget it. It's like well, I'm sorry. This line and this will come later.
Okay.
This comes now because there is a B, that is a zoom. and this, it makes sense to slides, but thank you for the point. So, yeah, right now is a kind of only marking the different regions I mentioned. So, and here is only a zoom of this region here, okay, just to see how the frequencies merge when they cross, okay, and basically the region of maximum nonlinear merging. So, it's a kind of going again the path I showed with the feedback regimes, okay. So first was the spectral information, then came the intensity information. We can also resolve the intensity with high enough value. We have 16 gigahertz scope. We have fast photodetectors. So what else can we say from the intensity time series? The thing is that now we can really see these picoseconds, so these sub-nanosecond fluctuations in detail for a lot of regimes. The point is that only small conditions, as before, give us some kind of distinguishable time series, no? But once you go, and here is only exemplary, no? Once you go really from not too far from threshold, you start to merge, and you have this kind of time series everywhere that you cannot distinguish visually anything that you say, oh, this is coherence collapse as usual, and that's all, no? What we do for this is to measure the autocorrelation, and using this measurement, we can extract more information. So, autocorrelation of a laser with feedback looks typically like this, so looks like this. And it has different echoes, different peaks at multiples of the delay time. I've not mentioned this before. In this kind of setup, we have a delay time of 75 nanoseconds. Typically, it's 10 meters something of fiber, and this signature of delay time is present in the autocorrelation. So what we do is simply use it. So we zoom here. We have enough resolution in our time series, in our long time series. We calculate autocorrelation. We center we make a zoom around this first echo of the autocorrelation, and we measure the maximum. Okay, we measure the height, and we do exactly what we did before. So if we change the feedback strength, now we change also the feedback strength for a given condition. This is only a given current. Okay, we compare spectral information and we compare information from the time series. Okay, and from this comparison, that's already enlightening. So how? Because you see that the crossing region, and now the horizontal line mentioned makes sense. This crossing region is the region where there is a drop. So you have good correlation, good memory, if you want, of the system to a delay time before. Here and here, maybe not so good here, but it's increasing. No? And the important thing, I think, what is really to remark is that there is a minimum, and the minimum is around the crossing region. Okay, the crossing region of the relaxation oscillation frequency and the delay-induced frequency shift. Okay? And we have used one parameter, which is the feedback strength. Now let's see how this information looks in more than one parameter. So feedback strength and also different currents. Okay? And when we see this, I mean, this kind of figure already claims that okay, you must do something with this because you have the same shape, but only a bit shifted and a bit scaled. So can you do something? Can you play with the time scales we have been talking and find the kind of relation between them? So that's the thing. So we use, as I mentioned before, the fact that different currents scale so the relaxation oscillation scale with the current, and the fact that we can also rescale the attenuation, and basically we simply define this ratio, which is the ratio between the increase in the relaxation oscillation and the increase in the feedback strength, and we keep it constant. So doing this, we basically are able to collapse all the data, all the curves, in a single shaped curve. Okay? So we do this, I said, so we're scaling the attenuation in a way that keeps this constant. And basically what you see is the minimum totally overlapping. And you could say, yeah, okay, well, the minimum is overlapping, yeah, but okay, what happens with the wings? The wings go crazy. So the curves have shifted in the proper direction, so now they are on top of each other, but they're not really on top of each other at the sides. But we say, if you analyze experimentally each one of the sides, so you make a bit more work, and basically you find that they fall on top of each other, really, but in experiments you don't see it, because you have an avoidable effect. For example, in the left side, which is the lowest feedback conditions, what you have is different, so you basically have lower intensity fluctuations, and then signal attenuation enters into play. So it's always there, no, but low signal attenuation give artificially low values of the autocorrelation. So here we have just characterized the maximum of the peak with respect to signal attenuation, and basically we see that it follows the trend we see here for the maximum. Okay. So if we could increase this, hypothetically, the curves would fall on top of each other also here. Okay. On the other side, the right side, the problem is different. There we have enough signal attenuation for all the currents. The problem is that this specific laser, when you are at this point, or at this point, or this point, or this point here, you have not all the time chaotic dynamics. You have the stability between chaotic dynamics and the stable emission. Okay, I've not mentioned before. I mean, what the points here and the points here correspond to stable emission, so correlation drop. And these points here only show that the average correlation has parts, so considers parts or includes parts of time series with chaotic dynamics with high correlation that would be on these lines, but also includes parts with lower correlations because they are stable emission like, no? And the average value falls on these lines. But if you wouldn't have this effect, then the curves would be on top of each other, as we will show later. We relate this with the fact that these lasers have really low value of line width enhancement, so alpha factor, and that this fact makes them less susceptible to feedback, or this stability to be. Yeah. There is another consequence of this. So basically, once we have this overlapping, and we have seen the information contained in the optical spectrum, so how the collapse happens there in this region here. So what we say is that, okay, this transition from high correlation values to low and again to high is the transition that happens in delayed coupled system, but for real feedback lasers, from weak to strong and weaker. And we say this. Now I could introduce some weaker. Really, these concepts are well explained in these two papers here, and also was introduced in a seminar on Thomas. So I will only say the consequence that they have on experimental data, because that's what I'm interested now on it. So in delay coupled systems, coupled with long delay, you would say, yeah, if they are in the weak curve regime, they can couple and they can show stable synchronization. If they are in the strong curve regime, their synchronization would be unstable. Okay? And we claim that this is a transition, actually because following this definition, we can demonstrate this. So we can, and we have actually set up this experiment. So we simply take this laser with feedback and couple half of the light, or part of the light, to another laser, which doesn't have feedback. So it's only coupled to the first one. No? So it's a basic synchronization scheme. And in this scheme, we have measured not only the correlation of the first laser, which is here in a black line, but the correlation that the second laser shows with respect to the first. And this kind, so this cross correlation between both is what is plotted here. And that is basically the experimental demonstration that this transition here is also a transition in synchronization. Okay? So this is already a kind of conclusive point here. But we don't restrict to one laser, let's say to this laser, specific laser, no, with this specific architecture. But we also have tried the same with a different laser. Okay, it's quantum well single mode laser, so these lasers only have one longitudinal mode of emission, but with different architectures, okay, that define this lasing emission, and both follow or fulfill this requirement, this scaling, this similarity of the feedback regimes. The nice thing is that this one that has a higher alpha factor also tells us that the effect that we saw here for low alpha laser in a higher alpha laser is okay. So the scaling is also perfectly visible for higher feedbacks. Okay. But okay, right now, so if you a bit of memory, basically we have used two of the time scales. So the relation between relaxation oscillation frequency and delay-induced frequency shift, we have kept this ratio constant, and we have scaled the dynamic regimes. Okay, so they fall on top of each other. So now we say that with respect to these two time scales, our dynamics are similar. Okay. The thing is that, well, that's not the whole scaling. That's not the scaling chaos I promised before, because actually there is a time scale that is not considered up to now. No? So now we include it. So we define this other ratio, which is relaxation oscillation and the external cavity delay time introduced before, okay? And use this new ratio to finally scale all the dynamics. So first, let's see how we implement this in the experiment. So we have this delay time, have this setup, and basically we unplug a part and we add a piece of fiber. Fiber is cheap, we can add how many meters you want. Well, we add 5, I mean, we need to control this, but one could do this much longer, or even shorter, so you can play with this easily. And we have initial conditions, okay, so one given delay time, one given current, and once we add the fiber, we have another delay time, and then we need to rescale the current properly, okay, with respect to this delay time. So once we go to the proper conditions, what we see is, yet again, this scales. So the dynamic regime scale, fantastic. But additionally, and that is much more even impacting, have much more impact, is that, of course, we have different delay times, so you need to scale the delay time, but once scaled, the autocorrelation functions are identical. So I show here only the first peak, but central peak, so all second peak, and so on and so forth, they all scale, they all fall on top of each other, okay? And basically the dynamics coincide, so we have the same dynamics in both. So you would ask me, okay, what's the recipe for scaling optical chaos? I would say, yeah, you take first you need to know the 3 time scales of your system. You need to know the dynamical, so the relaxation oscillation time scale. You need to know feedback-induced frequency shift. Okay, you need to know the external cavity frequency, and once you know them, you keep constant these ratios, and you scale your dynamics properly. So your dynamics will be scaled properly, no? So the autocorrelation will coincide. Actually, this okay, and this has really interesting properties and allows you to tailor the dynamics you want. So you are in one dynamic condition. So for example, you slow down your dynamics. You define or you look for a regime, dynamical regime, and basically you change then the delay time, and you can find another. So for another conditions, the same dynamic regime. No? So that's very important for that. Is particularly important, no? For any application. So you can in photonic information processing, you can target one conditions, no? Low current or low time scale, and then you do your computation there. You test it, and then you know that properly scaling it, you will have the same dynamics. No? Or in chaos communications, or in many applications. The only parameter that cannot be scaled this way is the alpha parameter, but it's not impossible to scale. I mean, you can modify alpha of your laser. Actually, it was demonstrated in this paper, changing. So that it's possible to change alpha. Okay, so then you can also play with this. So again, to show that this is not only experimental ideas or experimental results, I mean, it's supported by simulations. I mean, here, Blanco-Bayashi simulations, we show analogous pictures. We show the optical spectrum, so again, with a zoom here around this crossing region. See the drift here in the relaxation oscillation. I mean, this is not with respect to attenuation, it's with respect to feedback strength, so now it's linear. The relation of feedback rate and the frequency shift. And we see that, again, in the crossing region, well, it's not as before, no, one in front of the other, but in this crossing region, we have the minima here, okay, again, for the autocorrelation. And they scale properly with the change in the, or keeping the ratio constant between feedback rate and relaxation oscillation frequency. Okay, so model supports this, and this is a kind of, I would say it's a kind of test for the model, but okay, it's model inspired, no, at last, so very nice. Yeah, and the last part of the seminar will be a brief report of the application of these studies, this kind of study to quantum dot lasers. I mean, well, this is from a stay I had half a year ago in Amsterdam, where we analyzed the effects of delay optical feedback on quantum dot lasers. Okay, they had lots of quantum dot lasers there because, I mean, well, they are experts in modelling of multi-section quantum dot lasers, so they had a variety of devices. These devices are interesting because it's a different kind material, it's a different principle, so it's not quantum well gain material, is basically the quantum dots are your lasing emitting material, no? And they show much more broader spectrum than the quantum well laser we have used. They are not single mode, they are multi-mode. This is theory parallel structure, so they support lots of longitudinal modes. Above this, they have ground state and excited state emission, the dots. So they have different frequencies for the ground state and for the excited state. And as you see here, well, depending on temperature, depending on feedback rate, depending on injection current, their emission, so that's the optical spectrum here in nanometers, is different and varied, and really a lot of things can be learned and can be studied there. So the other thing is that their diversity and the complexity of the dynamics and everything that they show really makes that there's still not a consensus with the models. So there are many models and many claims in model, but not one leading, no, not one defining or having all the properties of laser with feedback. So that was a bit the motivation, also going there and trying to to find some guidelines that then you would follow if you want to design a model, no? You need to know. So I only show analogous figure again, okay? So again, maximum in the first autocorrelation peak versus attenuation, already rescaled with relaxation oscillation, okay? As a quantum well, let's say, no? Nice thing here is that even this device, this particular device, had 3 different populations of dots. As the feedback strength pushed, so increasing feedback strength pushed the emission to a single population, so we had only one population of dots emitting. There we realized that the scaling was present in this single population condition. Okay. Meanwhile, in more than one population of dots emitting, the rescaling was not present. Whatever the reason, we have not entered yet into detail of discussing this, but this interesting insight, let's say, that gives us energy, you know, the idea of following, because, okay, we have already one result that a model should be able to reproduce, no? So any model, this competition or variety of models should reproduce this fact, okay? At least for single population emission, quantum dots with feedback. Okay, so finally, hoping that, so not wanting to give you more into into the brain, simply 2 take-home message, or main take-home message. We have played with the 3 time scales. We say that we relate with different parameters you can control, and with this we have shown this similarity in the feedback regimes. This similarity allows us to identify the mechanism that goes from strong to weak and weak strong and weak chaos again in real semiconductor lasers. Okay. Second idea is that the full scaling with the 3 parameters of dynamics allows us to reduce dramatically the effort on characterization of the dynamics. Okay. So once we do one of these curves and we know everything that we need from the dynamic scales of the system, we know where we are and how to write to any other state. Okay. This has evident impact in the tailoring of the dynamics. So once you are in a specific state, you can slow down, speed up, whatever in the dynamics. You can push this state to another characteristic time scale. So you can do all this. We have proven this for quantum well lasers in experiment, more quantum well lasers in experiment, and supported by numerics also. And we have shown that this partially applies in quantum well lasers, at least when they are, that's partially, that's when they are single population emitting. Most of these results, except for the quantum dot stuff, has been set for publication recently. And okay, I hope that I've been able to to transmit you the illusion about these results, no? But if you are not from lasers, you can say, at least you think that, well, simplicity is always good, no? I mean, so thank you.
Thanks, Sean. Questions? Emilia?
I don't understand your transparency or slide on the scaling of the autocorrelation function. Is beta and is tau 1 and 2. I don't understand what here.
So the full, no? Or
this one. So what is tau 1? What is tau 2? And what is beta?
Yeah. So it's So this is the scaling factor. Let's say that if you have 2 different delay times. So you need to rescale all the parameters, all the time scales, let's say, in a way that the ratio is kept between them. No? So that's simply a kind of scaling factor that will be, so that fulfills the relation.
Now, so 1 and 2 are 2
different delay times. Yeah.
And then the claims, okay, this is quite triggering. The dependence of the autocorrelation function on the delay time is triggered, but then what is not triggered is that the dependence on the attenuation and on the injection is also controlled by this ratio. This is what you
Yeah, so actually in the first condition, the autocorrelation, the autocorrelation for a certain tau, excess current and feedback strength will coincide with the autocorrelation for the, let's say, scale, delay time, scale parameter, and the scale frequency time. So they will consider in this way. So.
And then, second question is, can this be shown, or at least in some approximated way, from some simple model, for example, the Lampo-Bayashi equations, that this is the case?
Yeah, well, it's supported by the model. So
no, but you only show numerical simulations. So if you do it, if you do it analytically, you can do it for weak feedback under strong approximation. So you would expect that only to be valid in a very small region. So in the end, the practical reality of it is way beyond what you can analytically show from a wave equation model. The real lasers actually behave more like it than the model.
More question?
Comments? Suggestions? If that's not the case, thanks again, Sean.